Hey guys, out of 7.2 we're looking at U substitution today. It's in your text 18F and G, and we're integrating composite functions. So basically we're trying to undo the chain rule. I want to show you working forwards through differentiation and then thinking about how you get back from there if you're integrating, and then same with this example, but I want to look at why this fraction in front is important. We'll do a little generalization and we'll go from there. So if we were to differentiate this, I know that the exponent drops by 1, also multiplies in front, and then this is the chain rule, so we're doing the derivative of the outside, and that's this piece, right? And then we do take the derivative, multiply by the derivative of the inside, and that's that piece, right? And then the 6 and the 3 can get together from this a term and this exponent. The 6 and the 3 multiply to the 18 that is in front. Fine. So let's take a look at that same idea with this one, right? It's basically the same. If we differentiated, the 1/10 stays outside, the 5 multiplies in front there. We're taking the derivative of the outside, all of this, so this decreases by 1, and then we take the derivative of the inside, this 2, right? What's nice about that is this 2 from the a term here and the 5 from this exponent, they make 10, right, when you multiply them. And this 10 and this 1/10 cancel out, right? And you don't see a value up here. There's an implied 1 up here. You don't see anything there because this was the reciprocal of this and this. So this is the reciprocal of this a term and the exponent, that new exponent. So if you were to work this backwards and try to differentiate the bottom equation that we ended up with, right? If we want to go from here and turn it back into here, I know that this thing came from this 2x plus 3. The exponent would have to be 1 greater. I know that we should, if we are integrating, we should have the product of the exponent, the new exponent, sorry, the 5, and the a term. We should have that in front, like that. But we don't. We see a single 1, so we have to have the reciprocal of this product in front here. If that's a little blurry, it's okay. We'll try a couple problems and you'll see the pattern. But that's the idea of where it comes from. So they walk you through in the text a whole bunch of reasons why this is true. And I wanted to kind of do that in a different light. They work like through a differentiation, but I visualize it like this. Let's look at this piece. So if you were to have a function like ax plus b to the n, and you were integrating it, it's not this one, forget about this for a second. If you were to integrate it, you'd get ax plus b. We're integrating, so you'll get 1 larger on the exponent, and so that's kind of a start, right? And I know, yeah, plus c out back. Plus c is pretty integral. So I know that it should kind of look like this. I know that this would be 1 bigger. And if you start with that frame of reference and then think about what would happen if you differentiated this. Well, this, I want it to turn back into this. Nothing in front here but a 1. So what we can do from there is say, okay, I know this would be multiplied by n plus 1 in front. Because if we were differentiating this going from here back to here, you multiply this in front and then decrease this exponent by 1. Okay, fine. And also I know that then because of the chain rule, we'd multiply by the derivative of the inside, which is just a. Right? So I think if we differentiated this as it is, we'd have this n plus 1 and a term. But we don't see it here, right? There's no n plus 1 and a term here, which means that there was something in this original piece that canceled this and this out. And the best way to do that is by multiplying by a 1 over n plus 1. Eraser. Multiplying by a 1 over n plus 1 to get rid of this, and multiplying by a 1 over a to get rid of this, right? And that's why this becomes 1, this becomes 1, and if you differentiated it, you don't see any coefficient in front here. You just see this piece. So where that leads us is this. I think you can say that if you're integrating this ax plus b to the n, you get that with nothing in front, you get this piece. I know we're increasing this by 1, but you also get 1 over that new exponent and 1 over the a term inside, or 1 over the derivative, if you will. And so that's where this comes from. Eraser time. So that's where this piece comes from. He said, here's my function, and here's the integral. This has to be the integral because we increase this by 1. That's not a big deal. But if you don't if you don't put this in for the integral and this in for the integral, when you differentiate back to this original function, you have this n plus 1 term out in front and you have an a term out in front. We don't see it here, so you had to have this fraction and this fraction, right? That fraction is this, sitting out there. If you're still a little blurry, we'll do a bunch of problems and you'll feel a lot better. But hopefully that you can kind of see where that's coming from. This is the same sort of thing. If we were to differentiate e to the ax plus b, the integral is the same sort of idea as the derivative, in that the derivative should be e to the ax plus b, but then you need to multiply, because you're using chain rule, you need to multiply by the derivative of the inside, which is just a. We don't see an a here, right? So if you didn't have this piece and you were differentiating back to here, you would have an a term in front. We don't see an a term, so that implies that we had 1 over a in front to begin with. All right. Same with these other pieces. This 1 over x tells us that we're going to be looking at a natural log, right? Because the natural log, if you took the natural log, the derivative is 1 over x. But then also, because it's chain rule, there's something inside, we have to multiply by 1 over that a term. Same with cosine, right? Derivative of sine is cosine, and you'd multiply by the a term generally, so we have to mitigate that by saying 1 over a. Same thing with the negative cosine. Derivative should be sine, but chain rule says you'd multiply by the a, so 1 over a is there to get in the way of that. This is what it looks like in your, it seems like that always pops up. Get out of here. This is what it looks like in your formula booklet, like that. Just in a different order, but it's the same idea. So let's try one out. If we wanted to take this, I know that this came from, let's move this down a little bit. I know that this came from this piece, right? If we were going to integrate this, your exponent increases by 1. If you didn't know that this was here or this here was here, and you're going to re-differentiate and turn it back into this, you would get a 5 out in front. You get 5 and the guts. This would decrease by 1 back to where we'd expect it to be, and then you'd multiply by the derivative of the inside, chain rule. I don't see anything here, so that means that there must have been a 1/5 to cancel out with that 5, and a 1/2 reciprocals, right, to cancel out with that 2. And so we're just left with this piece. So that's what this 1/2 and this 1/5 is. You can put it out front, put it underneath, it doesn't really matter, right? Plus C at the end. And so it looks like this, the 1/2 and the 1/5 to get together and make a 1/10. All right, let's try it with this guy. Let's change his format up a little bit so it looks a little nicer. Call it, instead of the square root, we're going to use half. Instead of the denominator, we're going to use a negative. That's a little more straightforward to use. I know that if we integrated if we integrate this, we're going to get this part, right? The exponent increases by 1, so it goes from -1/2 to a +1/2. That's not a big deal. And if we just took this and differentiated it, we should get this back. But if you differentiate this, you get a 1/2 out front, and then the inside bit, and then you'd get this -1/2 as you decrease this by 1, and then you take the derivative of the inside and get times -2. So there has to be the reciprocal of this outside, because we don't see a 1/2 here. There has to be a reciprocal for that, and there has to be a reciprocal for this, right? Not the opposite reciprocal, same sign reciprocal. So that's what this piece is. Let's see, so this is this piece, and this divided by a 1/2 is multiplying by 2. So they have the same sort of thing, but I don't love their format. I love my format better. Take it or leave it. But the same things are there. They like this, just divide by, it's in this notation, right? It's in, put the whole thing over this n+1. That's great, but I don't like to memorize junk, and this is what I remember. So this is this, and this is 1 over this piece. If you clean it up and change it back into radical form, there she is. Cool. Let's try some tougher pieces. So let's try this. What we can do is break this up and integrate each piece individually, which is nice. So you can say that this piece, the 2 is just sitting outside, and we would take the derivative of this, which is itself. But if you integrated back, you'd take the derivative of it, but you'd also multiply by the derivative of that exponent, right? So you'd have a 2 there. I don't see that extra 2. I see this 2, it's right there, but I don't see this extra 2, so that's why we threw in this reciprocal 1 over 2 to cancel these out, right? So that's what this piece is. It's making sure we don't see the derivative of this if we were to redifferentiate. So there's the derivative of that first part, and then the second part is really similar, right? So you'd say, all right, well, this is, I know that the e to the x will have itself as its integral and derivative. If we didn't know this was here, and we redifferentiated it, we'd get e to the -3x times the derivative of the exponent. We don't see that here. There's no -3 there, which means that there was something in front, just 1 over that derivative, to cancel it out. Cool, and then you could clean it up if you wanted. These multiply, make sure you get the c in there, and you're good to go. Same sort of thing here, except with the 4 here, we can just move, it's this way, move the 4 out of the picture. You can integrate, the integral of constant is just that constant times the integral. So we clean it up by moving the 4 out of there. And I think we talked about that in the last video. And then you can differentiate this, right? You could say, well, I know that this piece, this comes from a natural log, right? If you differentiate natural log of a, if you find that was y and you're finding y prime, you'd call this 1 over a. So you can go from there and say, well, this whole thing, if you integrate it, should be this whole thing, right? This 4 is still minding its own business outside. We'd also, so if we differentiated this back to this, you'd have natural log of the guts is 1 over the guts, that's fine. But you'd also take the derivative of the inside, so we can say we would expect to have a -2 sitting here. We don't have a -2 sitting there, and it's because of this extra part, 1 over that -2. So we can clean that up, and it looks like that, right? The -1/2 and the 4 get together, and you're set. All right, so for this G part, we're looking at integration by substitution, and there's an interesting derivation of where this comes from, but this is just a sneaky trick when you see an integration and there's a function and its derivative inside being multiplied. So the derivation uses FU, and I kind of like that. And I was going to walk you through it, but it just takes a long time. In the end, this is what is up. If this piece. If you are looking at an integration, you see some function u, and you see its derivative. The du dx is the derivative, and that can cancel out with the other dx. That's usually in this integration, right? And so you can integrate a simpler problem and find fu du instead of this whole thing can basically be canceled out. So if you see a function multiplied by its derivative as you're taking an integral, you can call the main function u. You recognize this piece, and you recognize this a second chunk as its derivative. You can play this game. Let me show you how that works. We're integrating this mess. I noticed that this, if you took the derivative, you'd get this, right? So this is what we're going to call u, and this is what we're going to call du dx. I think we probably wrote it here. Okay, there's u. You're going to choose u as the original function, the piece you want, and du dx is going to be the derivative that you recognize. Okay, if you switch this one around, right? I'm going to switch places with these by multiplication. You're left with dx is this. So instead of calling dx dx, we can throw this in there. And so it'll look like this. Here's 2x, still there. Instead of all of this, we called it u, right? We called it u. And instead of dx, we called dx du over 2x. And there's a shorter version of this. I just want you to see the mechanics. That's nice because these cancel out, and you're just left with this. All right, u to the 10th du, and that's easy to integrate. We're using a different variable, right? We're not using x's anymore. We're using u. But if we integrate this, you can see that the integral would be 11. You increase this by 1 and then divide by or multiply by 1/11, right? So that's where this comes from. But it wasn't u, it was x squared plus 1, and so we can put that back in. Don't worry about this. This was the original, and just say this is u to the 11th over 11. Okay, so let's try it out. Even if they didn't tell us to use substitution, if you looked at this with your nerd goggles on, you'd see this piece inside, right, and its derivative outside, right? If you derive this, you'd have 3x, drop the 3 by 2, you'd have this piece, and you'd get rid of the x, and you'd have this piece. So you have a function, u, this piece, not necessarily in the radical, just look for it as a packet, and its derivative, so this is du dx. Yeah. So if we call it such, right, if we call this part u, and we call this part its derivative, then here's u, still in the radical, right? This part. And here's its derivative outside of the radical. We're just renaming them. Cool. What's nice about that is it doesn't exactly work like this, but those dx's essentially cancel each other out, and you have u to the half. We're just changing this around so it looks different. You could still call it radical u. U to the half du. And that's nice because that's easy to integrate, right? You'd integrate that by saying, ugh, I hate that notation. You'd integrate that by saying you'd up this by 1 whole unit, so now it's 3 halves, and then you'd multiply by the reciprocal in front, 2/3, right? They have the same thing. Oh, plus c, plus c. They have the same thing, except they divided by the fraction, and if you divide by the fraction, you'd multiply by the reciprocal. So I think this is awful, and I like this much better. I think it's smoother. And then instead of calling this u, we're going to reinsert u, and u was this to begin with. I got to get my colors straight. Cool? Bam. So u substitution, really nice when you have function and its derivative multiplied inside a radical. Fairly specialized, but you can be sure that the IB will be happy to throw you tailor-made problems like that. Okay, so we're going to do a couple more examples. There's 2 here and 2 here, and we want to integrate this. If you look at this piece, you can see that this, it could be a function, and this would be its derivative. So you could maybe rewrite it if you wanted like this, right? Still, here's my function, and here's the derivative thereof. So might call this piece u, and therefore this piece would be du dx. Just means the derivative of u with respect to x, because we're calling this thing u. All right, and so that's all this. This is the red part, and this is the green part. So really this is 1 over u times its derivative. Essentially these cancel out, and you're left with 1 over u du, which just means integrate 1 over u. And so that should give us natural log of u, absolute value of u, plus c. And that's nice because then we can just reinsert u into that spot. You end up with that. Nice. All right, let's try that with this. Get rid of all this stuff. Don't look, avert your eyes. Sorry. All right, so integral of x times this mess dx. Now, you can kind of hone in on this piece and say, all right, I see inside of here, I see inside this in the exponent 1 minus x squared. You can think about this top part being u. And this is the hardest part of u substitution, recognizing that you have a function and its derivative sitting there. Let's call this u. If you were then trying to find du dx, which is just the derivative of that, the derivative would be 0 from this piece, du dx, 0 from this piece, and then minus 2x from that piece. So I'm looking around in this equation for a negative 2x, and I don't see it. But we can sort of engineer things, if you will. This is half of this. It's 1x. We need 2x, needs to be negative, so it's negative a half of du dx. Right? I'm looking for negative 2x, and I only have a half of it. Happens to be negative, happens to be the opposite sign. So what we could do is inject that negative a half into here and say, maybe do this in a second step, call this negative 2x times negative a half, right, inside the integral times e to the negative 1 dx. Right, I might make that as an intermediate step. This negative a half times negative 2, we haven't added or we haven't changed it at all, right? Negative a half times negative 2 is still 1, this 1 that's in front. Here's our x. If we now pull this out, integrating a constant, you can just pull it out front. And this is that derivative we're looking for, which puts us into a good spot for this substitution, because now we see a u here and u's derivative, right? So we have u and du dx. So that's what this part's about. Negative 1/2 sitting happily outside. We're calling this part u. We're calling this part du dx, u's derivative. And so now that we have e to the u, a function times its derivative, these can happily cancel, kind of, and you're left with this. And then you can just take the integral of this, which is a lot easier, right? The integral of e to the u is e to the u plus c. Oh, and half is still there, right? So this is that. Yeah, well. Yeah. Great. So now we can say that we have u was this guy, and so we're going to re-plug this in. Substitute. We use plug in all the time. It's substitute. And you should get that. Bing, done. All right, here we go. If you still don't understand what u substitution is, let's try 2 more. If you got it, go ahead and run. Try it out. So here, cosine cubed x sine x dx. I see in there that we have, you could maybe rewrite this. I don't know if they've actually rewritten it this way, but I might rewrite it. Yeah, sweet, great. Rewrite it as cosine x cubed and sine of x. What's nice is I can see that these are integral or derivatives of each other, and you could probably do this either way, but I think that it's easiest if you call cosine of x the u. Then if you use u as cosine of x, the derivative of cosine is negative sine. This isn't quite here, right? This is sine, not negative sine. So really we don't have the derivative, we have the opposite, the negative derivative. Here's u, here's du dx, the derivative. And so that negative can be floated outside, just like, it's gone, just like this half, negative half gets pulled outside. Yeah. This is the same sort of thing, where this negative can be floated outside. You're integrating a constant, negative 1. And then you can resubstitute in your u. Oh, sorry, integrate first, man. Integrate first. So increase this by 1, and constant out front 1/4, or just divide by 4, that's fine, plus your c, and then resubstitute u into there. So it should look something like that. Oh, now they do the 1/4. All right, let's try one more. One last one. Cosine x sine x. Maybe rewrite it. I guess you don't have to rewrite it. What I would maybe think about this as, let's undo that. I guess I would rewrite it. Let's rewrite this as integral of 1 over sine x times cosine x dx. dx just means with respect to x. So I think that this will be u, so u is going to be sine, and this is its integral, right? So du dx. So u is just going to be the 1 over sine. So I think that's what this is from. Yeah, so 1 over sine, and this is the integral of, the derivative of that. And then your dx's can cancel, and you'll just be left with 1 over u du, which means integrate with respect to u. The integral of 1 over anything is the natural log of that, and then plus c, absolute value, and then resubstitute your sign. Cool. So there you go. That's integration by substitution. Do it when you see a function and its derivative. And don't worry that the function's in a radical or in a cube or in whatever. Just look for any packet of that might be a function and a packet that might be its derivative multiplied. Good luck!